Hello and welcome back, everyone. Moving on to chapter 1, really the second chapter in the book, titled Linear Algebra. Some of you may have already taken a course in linear algebra. Those of you who haven't, that's why this chapter exists. So it turns out that linear algebra plays a fairly fundamental role lying underneath multivariable calculus. You don't need to know absolutely everything from linear algebra. That's why it's not necessarily a prerequisite, but there's a pretty good collection of ideas that we should know before we head into really defining derivatives or some multivariable differential calculus as a whole. So here we are, and I just want to start out in the first section with the question, what is linear algebra? And if we think all the way back to our early courses in algebra, right, you may think that linear and algebra are both easy topics, right? Linear being linear functions like y equals mx plus b. Algebra maybe being solving quadratic equations, for example, ax squared plus bx plus c equals 0. Turns out linear algebra is more complicated than both of these. Mathematicians simplify the two of them, linear systems, down to a single dimension when you're learning about them in high school. Similarly, algebra, we're only talking about the algebra of real numbers in high school, so lots of things get quite harder when you're no longer working with just the algebra of real numbers or just linear objects in one dimension. So here in the linear algebra, we are going to still talk about our favorite y equals mx plus b, meaning if we were to graph y equals mx plus b, it may look something like this, where m is the slope. And you'll recall, what is the slope? That's the rise over the run of this plot. And b is the y-intercept. And these objects were called linear because the first four letters of linear are line. So these are the objects which draw lines when plotted in the xy plane. So the primary reason why we like to study these objects, y equals mx plus b, or if we want to write it in function notation, f of x equals mx plus b, is that it's pretty easy to invert this function. Let's recall what it means to invert a function. If we invert y equals mx plus b, we're going to swap y and x around, and we're going to solve for y. How do we solve for y? Well, we have to subtract b. We have to divide by m. And so your inverse function ends up being x minus b divided by m, and all you needed to do to get to the inverse was perform one subtraction and one division. More importantly, if I consider this inverse function, and I kind of distribute m to both of these terms, to the x and to the b, it turns out the inverse function takes the form, it's got some new terms on it, but it really takes the form y, which is f inverse equals m, some new m, this happens to be the reciprocal of the old m, x plus a new version of b, right? So there's still just a slope and a y-intercept. In other words, the inverse of a maybe one-dimensional line is a one-dimensional line. So these functions, y equals mx plus b or f of x equals mx plus b, are really well behaved under inversion. And what that means is you can solve linear equations quite easily. The solution to linear equation is a linear procedure. And that's why it's kind of the first function that we experience in high school. Now I wanted to switch gears really quickly, very slightly, to recall kind of the primary motivation of differential calculus. When we were originally learning about differential calculus, we've got some function here. And the entire point of the derivative was to establish a specific point on the function, call this point maybe x naught. And then you wanted to find the tangent line to the function. The tangent line has the slope f prime. And so the tangent line in some ways is the primary object of differential calculus. And you can establish the slope of the tangent line by computing the derivative. Or in some ways, that's the definition of the derivative, is the slope of the tangent line. And so these objects of lines with slopes are kind of integral to, no pun intended, integral to calculus, right? They're one of the most important parts of calculus is establishing lines which approximate functions. So that's why we're going to study lines, or really the higher dimensional versions of lines, and in some ways that's what linear algebra is. So I'll answer it a little bit more later, but for now I'm just going to say linear algebra is the study of higher dimensional equivalence of lines. Hence this word line inside of linear algebra. So what do these higher dimensional equivalents look like? I've got a few examples here. Here's my first one. Suppose I have two inputs to f, so I'm calling it f of x and y. Well, if I've got two inputs, I'm going to end up with 1, 2 slopes. So there's the x slope, and there's the y slope. And what does this final term b mean? This final term b, in at least a case where we have two inputs, so you have x and y's inputs, b will be the z-intercept. And what this object actually is as a whole, this object is a plane embedded in 3D. Of course, a plane being still a flat object, somewhat similar to a line, but now we have a two-dimensional line. You get even more complicated than that. My next example, G here. Notice I've bold-faced G, and then I have 1, 2, 3 inputs to G. So G is bold-faced because it has itself 1, 2 outputs, and it has 1, 2, 3 inputs. There's my 3 inputs. And of course, each of the inputs is associated to its own slope. These are the input slopes in the first output. And we could potentially have different slopes in the second output. And in this sense, each output is also allowed to have its own individual intercept, right? Separate intercepts for each output. But in some ways, everything is still behaving similarly to y equals mx plus b. We still have mx or my or mz, some slope against each of the inputs, plus a b in every single output. So these are still flat objects. They're just occupying much higher dimension, 3-dimensional input and 2-dimensional output here. Or in my last case of h here, I've decided to put n inputs, and I've decided to include many, many outputs. So in this case, n minus 1 outputs. But you can imagine as many inputs or as many outputs as you would want, as long as every subset is a version of that mx plus b. That's what we're looking at. So these are the higher dimensional equivalents of lines, and these are what we study in linear algebra. We study these functions. The question is, what sorts of properties do these sorts of functions satisfy? And before we get into that, I do want to talk about, there's this very subtle difference between our words linear and affine. Because it turns out that this notion of y equals mx plus b is not technically linear. It is affine. Okay, and we'll talk about the difference between the two of those very briefly. So a linear function is going to satisfy if we decide to take 1, 2 inputs added together, and each multiplied the output ends up being 2 outputs added together, each multiplied by the same multipliers as the inputs. Okay, so A and B haven't switched around between these two cases. So that's what it means to be linear, and I'll show you why, using that definition of linear, y equals mx plus b is not considered linear. So I'm going to jump down to this region, and I just want to show really quick that if I do something like 2x plus 3y inside of mx plus b, that's going to be m times 2x plus 3y plus b. Well, the m can go ahead and distribute, so we get 2mx plus 3my plus b. And so we do gain the multipliers, 2 and 3, which were our original multipliers, but we don't have 2 copies of mx plus b and 3 copies of mx or my plus b here. Right? What I would need, this entire f of x on the right-hand side, or this entire f of y on the right-hand side, would just be mx plus b or my plus b here. Well, because of the way that maybe the 2 would distribute to b, or the 3 would distribute to b, that's not 5b there. This is not 5b. And so the b is what's getting in the way. It's kind of this action of the multipliers not interacting with b. So I'll just say notice multipliers 2 and 3 don't interact with b. And that gets in the way of y equals mx plus b being a linear function. Now, not a big deal that you perfectly understand what linear is. I just want the main takeaway is that, you know, linear functions only add and multiply variables, but not constants. Okay, you can't add or multiply constants for linear functions. And the plus b, of course, being an additive constant. Something to get used to. I know the language is different from what we've had our entire lives. You have to drop b. So if you want something linear, y equals mx is linear, y equals mx plus b, because we're now adding a constant, it's not linear. And this is the word affine that we have. So it turns out an affine function is just always the sum of a linear function and a constant. So if you add a constant to a linear function, you recover an affine function. What does affine actually mean? It means that you've translated, right, a linear function, y equals mx, for example, necessarily passes through the origin, right, because that plus b is the y-intercept, and if b is 0, then the origin is the y-intercept. But if I translate this, that's going to be my affine function. So some translation of a line that passes through the origin. Now, it turns out that the theory of both functions is kind of equivalent. But the reason why we focus on the theory of linear functions in the sense of linear algebra is that the theory itself gets slightly easier. Like the statements are less complicated. Statements that we make are less complicated due to dropping additive constants. So we drop the additive constants, and that just means that the statements we can make are less complicated. If you were to invert the function y equals mx instead of y equals mx plus b, the inversion of y equals mx is just 1 divided by m times x, right? The inversion, you take the reciprocal of the slope. And so you don't have this weird additive b that you have to take care of. And so the theory just ends up getting easier with linear functions when you don't have the plus b sitting around, and that allows you to kind of make broader statements. And then if you ever want to apply them to affine functions, you can. Okay, so I'm not going to go through the next proposition, even though it's nice. What the proposition says is that if I compose linear functions together, the output is necessarily linear. Okay, so this is really what I'm trying to state here. The same proposition is the same as these 3 bullet points. So what I'm saying is that adding to linear functions gives a linear function. I have composing to linear functions gives a linear function. And finally, scaling. Scaling, we mean multiplying by a constant, gives a linear function. Now, why is it important that all 3 of these are true? Well, mathematically speaking, when we use this word algebra, we're not referring to high school algebra, where we're manipulating variables and coefficients to solve equations. When a mathematician uses the word algebra, they are describing a collection of objects upon which an addition, a multiplication, and coefficients can be well defined. And it turns out in the context of linear algebra, we're describing linear functions as the functions which can be added, which can be multiplied, but really in linear world, this should be composed. So we're composing linear functions, and coefficients are scalars, or, you know, constant multiples. And so mathematicians, when we say linear algebra, we're saying that linear functions have the ability to be added, they have the ability to be composed, they have the ability to be scaled, and you still recover a linear function after operating in those 3 different ways on these objects. And so algebras are spaces within which these 3 ideas of addition, composition or multiplication, whatever you want to say, or coefficients or scalars, whatever you want to say, preserve kind of the overall structure of the object. It's a very abstract notion. This is why courses like abstract algebra are actually included in an undergraduate math curriculum as well. It's because algebra is much more broad than what we like to normally give it in high school. So I've got this next remark, which basically says, from now on, we're going to consider linear functions. We're not going to consider the affine functions. It turns out the affine functions, if we ever choose to consider them, and we will once we get to differential calculus, they're just kind of a direct consequence of studying the linear functions first. So we're going to study the linear functions for the rest of this chapter. Now I've got a nice definition here that you've probably seen before. The definition is of inverse functions. But now we're going to describe inverse multidimensional functions. So in multidimensional functions, inverses behave the same in multiple dimensions, but we need to make sure that we interpret these boldface x's as multiple variables. So they're getting multiple variable inputs and multiple variable outputs. That the inputs, outputs both have dimension n, right? Or whatever dimension my functions are mapping. So an example of this would be something like f of x, y, and z needs to have three outputs. So we'll say maybe f1, x, y, z, f2, x, y, z, and f3, x, y, z. And then the inverse, if I took the inverse function of the forward function of f of x, y, and z, what we want out of this is we just want a single x, a single y, and a single z. So three inputs and three outputs in this case. So there's the 1, 2, 3 outputs, but if we take the inverse of this, the inverse needs to have the ability to take three things into it, and then the inverse outputs three objects as well, but those objects should be exactly x, y, and z. Okay, now why is this important? Why are inverses important? Well, it turns out every time we decide to solve equations is inverting a function. So solving equations and function inverse are the exact same thing. I'll show you why right now. So let's just consider this equation, 4x plus 7 equals 3. The way you would solve it for x, I think you all know how to do this, is you subtract 7 from both sides, cancels with that 7, you're going to end up with 4x is negative 4. You're then going to divide both sides by 4, and you're going to recover that x is equal to negative 1. Now, why is that the exact same as inverting a function? Let's think about the original function, 4x plus 7, no longer equal to 3. Let's just say this is equal to y. Now we have a y equals mx plus b situation. And if I wanted to invert this, I'm going to swap y and x around. 4x plus 7 now equals x. I'm going to solve for y, which we saw earlier. We're going to subtract 7, and then we're going to divide by 4. Let's think about the original equation we wanted to solve had a right-hand side of 3. What's going to happen if I just plug that 3 in for x? Plugging in 3 for x there, it says y is equal to 3 minus 7 divided by 4. That's negative 4 divided by 4. It says y is equal to negative 1. What was our solution? Our solution was negative 1. So it turns out that inverting functions and solving equations are really the exact same procedure. It just turns out that inverting functions, you're keeping variables around when maybe you don't need to. Why do we care about function inverses then? In a linear algebra context, why do we care about these multidimensional inverse functions? Well, multidimensional equations look like this. Here is an example of a multidimensional equation. It's really a system of equations, right? We've been working with these before. This is a system of equations. We've been working with multidimensional equations before, we just never necessarily called them multidimensional equations. We called them systems of equations. So what would it mean to invert the function that represents this equation? Well, we first have to understand what we mean by the function of this equation. Let's look at this equation first. We decided that the function was the left-hand side, right? So f of x here is 4x plus 7. If we think about our systems of equations, we're going to consider the function the left-hand side. But if we want to restrict to linear functions, we can only consider the function as the terms that don't have additive constants. Okay, so if we want to do linear, let's say linear functions, on the left, what do we have? We have the function f of x, y, and z, but now f is multi-valued. It's a multivariable function. It has one output. What is the first output of f? It's x plus y plus z. What is the second output of f? It's 2x plus 2y minus z. And what is the third output of f? It's negative x plus 3y minus z. So f has 3 inputs and 3 outputs. And we're going to want to invert f. Finding f inverse will allow us to solve this system of equations. So that's going to be kind of an overarching idea of linear algebra, is going to be some way of computing f inverse given some linear functions so that we can solve equations. Now in this case, for the example I just provided, it turns out the inverse function happens to be 1/12 x plus 1/3 y minus 1/4 z as the first output of the inverse, 1/4 x plus 1/4 z as the second output, and 2/3 x minus 1/3 y as the third output. Now, if you just decide to act the inverse function on the inputs 1, 5, and 3, meaning that I'm just going to plug in 1 for x, five for y, and 3 for z. Once I plug all those in, my inverse gives me the output 1, 1, negative 1, which I interpret as an x solution, y solution, and z solution. 1, 1, negative 1 is the solution. Now, if we go all the way up to the original system that we had here, if I choose 1 for x, 1 for y, and negative 1 for z, 1 for x, 1 for y, negative 1 for z, and 1 for x, 1 for y, negative 1 for z. Let's see if these are actually true. What is 1 plus 1 minus 1 plus 1? Well, I got 2 there. Minus 1 brings me down to 1, plus 1 brings me back to 2. If I have 2 times 1, that's a 2, plus 2 times 1 is a 2. So that gives me 4, minus negative 1 gives me 5, and then minus 1 brings me back to 4. And then I have negative 1 plus 3 gives me to 2, minus 1 minus negative 1 gives me up to 3. And so finding the inverse does allow me to solve the system. Now, all of this for now is probably really fast. We're not actually worrying about it. We're going to study linear algebra. We're still trying to motivate why linear algebra is important here. If you don't know how to find that inverse yet, totally fine. This is what we're spending the entire chapter on. But I did just want to point out that that's really the motivation behind us studying these linear functions, is to solve systems of linear equations. Now, the next proposition is quite useful. It's going to say that whenever we're trying to solve a linear system of equations, at most, we're just going to have to work with other linear functions. So linear functions solve linear equations. Very nice to know. This is why linear algebra is still important. But how are we actually going to learn about all of these objects? We're going to learn about all these objects not using linear functions directly. We have a shorthand notation which greatly simplifies how we understand linear algebra or linear functions, however you want to think about it. Linear algebra and linear functions are kind of the same thing. It's the algebra of linear functions, right? Okay, so what is the shorthand going to be? Well, the shorthand is matrices and vectors. And some of you may have, especially if you take a linear algebra class, you know about these. And some of you, if you haven't taken linear algebra, you've probably worked with both matrices and vectors. Vectors are very common in physics courses. Matrices can sometimes be introduced in math courses for different reasons. But matrices and vectors are our shorthand for actually studying linear algebra and actually solving linear equations, computing inverses of linear maps, etc., etc. So how are these going to work? Well, let's start out with a system of linear equations again. This beast of 6 equations in 6 unknowns gets pretty ugly, right? Like, the more we could jump up to 100 dimensions if we wanted to, and we'd have 100 equations with 100 unknowns, and we really don't want to represent it just as a massive curly bracket and then a bunch of variables sitting around all equal to a specific number. There's got to be a better way, right? And so what matrices and vectors are going to try to do is they're going to isolate the coefficients for us. The point of matrices and vectors is to isolate coefficients, and I'll say which are the only important parts of linear equations. Why are they the only important parts? Well, variables are kind of just assumed to be there. You would notice if I physically removed every single variable here and I just kept the spacing the same, I kept all of the spacing the same in this system, you would still retain the information that I currently have. I mean, maybe not completely. I would have to include spaces where there are zeros, which you see me adding below here. So you would have to include the zeros in front of some of the variables that maybe didn't appear up top. But aside from that, if we look at the bottom representation of the system, we can see that the coefficients 1, 2, 3, 4, 5, 6, 6, negative 5, 4, negative 3, 2, negative 1, 2, negative 2, 1, negative 1, 0, 0, 1, 3, negative 1, negative 3, 1, 3, 0, 0, 1, 1, 1, 1, negative 1, 0, negative 3, 0, negative 5, and 0. All of those coefficients uniquely determine the left-hand side of this system. So just the coefficients alone, uniquely determine left-hand side. And kind of in a similar vein, 21, 3, 0, 4, 4, negative 9, you can interpret those as coefficients or constants. Coefficients or constants uniquely determine the right-hand side. So by considering only coefficients on the left-hand side, only coefficients on the right-hand side, we preserve all of the information. And what does the system actually look like? The system can look like this. Maybe it's not that much nicer. I mean, it's still a lot of numbers, but they're grouped in a fairly recognizable manner, right? A fairly nice grid structure. I've got all my variables here. And it's basically like input and output. So everything is quite clear where all the inputs are, where all the outputs are, and what my variables are doing. And what are these objects that I've drawn? Let's actually jump back here. These objects are all something phrased in what's called array notation. So array notation, or a two-dimensional array notation, it's a technique consisting of placing mathematical objects, and these are often numbers, which we see, within round, square, or curly brackets. And they're going to be equally spaced in horizontal rows and vertical columns. So if I jump all the way back down here, what do I have here? I've got some round brackets or parentheses, however you want to call them, and I've equally spaced my mathematical objects in rows and columns within these brackets. That's called array notation. And of course, I've got other examples here where I've used maybe more elaborate math objects. I've got the tensor product there. I've got aleph there, pi, whatever. You can put anything inside of an array if you want. It's simply a notational technique. But what's more important is that these array notations are going to allow us to rewrite very large systems of equations into somewhat condensed notation. Now, we're going to exclusively use round brackets in the text for our arrays. Most texts will either use round or square brackets. I hardly ever see the curly brackets, but just be aware that they could happen now and then. Anyway, this is basically what we're going to be thinking about when we think about matrix and vector representations, is translating a system of equations or maybe a function into an array. So let's actually talk about what a matrix representation is. A matrix representation is a translation or a re-representation of a linear function as an array. So what I have here in the top is a linear function. Now, it's kind of an arbitrary linear function, so it looks enormous and kind of ugly, but it's an arbitrary linear function where the inputs are x1, x2, all the way to xn, and now the outputs are sums of x1, x2, all the way to xn, multiplied by coefficients, right? So kind of the important objects that I'm going to keep talking about here are still the coefficients. Coefficients are the fundamental object to linear algebra. And so I have all of my coefficients here. I kind of hate having to represent everything as a function all the time. All I'm going to do to create a matrix or a matrix representation of my linear function is to place the coefficients into an array. And once I place the coefficients into the array, by the way, preserving order, once I place them into an array, I have this object, which you could either call an array, it is an array, but the moment that the object, an array, which represents a linear function, so the moment that we're associating in our minds the array to a linear function, an array which represents a linear function is called a matrix. Every time we see this word matrix, we're referring to an array that represents a linear function. So there's always a linear function hiding behind the matrix. And that's kind of what's important for linear algebra as well, is to recognize that it's always a linear function. And so how do we actually perform matrix representation? Well, what I have here is a linear function f. It has three inputs, x, y, and z, and it's got two outputs, x plus 2y minus z, 3x plus 3y minus z. How do I construct a matrix representation of my linear map? I'm just going to look at the coefficients, which are 1, 2, -1, and 3, 3, -1, and I'm going to directly translate those coefficients from the first output into the first row. So I'll say first output goes to first row. And what do you suppose I'll do with the second output? The second output will go to the second row. The coefficients of the second output to the second row. So that's all I'm going to do for matrix representations. I can do the same with the next function I have here, g, mapping x, y, and z to x plus y minus z, comma y, comma 2x minus 2z. So the first coefficients, which are 1 and -1, should end up in the first row, 1, 1, -1. The second coefficients, which are, well, here's a y, right? It's just a y, but really y is 0x plus 1y plus 0z. I think it's important to recognize that the coefficients on x and z are still there, even though you can't see them. We have coefficients of 0, 1, and 0. Those are going to end up in the second row. And finally, 2x minus 2z really should be reinterpreted 2x plus 0y minus 2z. We're going to take our coefficients 2, 0, and -2 and include them in the third row. These representations really not too bad. Finally, I've got h here, which only has one input, but it still manages to have 1, 2, 3, 4 outputs. These outputs can be interpreted as combinations or coefficients on the input x, in the sense that the first coefficient is -2, so the first row gets a -2. The second output has a coefficient of 3, so the second row gets a 3. The third output, 0, is the same as 0 times x, right? And so the coefficient there is 0, so we have a 0 as the third output, and the coefficient on x in the fourth output is a 1. And so this linear function does also have a matrix representation, although it just looks like a vertical strip or a vertical column. Is still a matrix. It doesn't actually need to occupy more than one column to be considered a matrix, but this is a matrix which represents the linear map that just has a single input. So now we should actually analyze this last matrix a little bit more, -2, 3, 0, 1, because if I jump all the way back to the system of equations, when I translated both my variables and the coefficients I wanted everything equal to into array notation, those both became single columns. And what we just encountered was a matrix which had a single column. However, there's another way to interpret single column arrays, and this is as vectors. And so what are vectors? Well, we're not really going to talk about this definition for vectors because it's a little bit ugly and it gets more abstract than we need it to be. So I have a remark here: do not spend too much time in this course trying to internalize the previous definition. What are vectors? I have in the next example the quote-unquote definition. Not the true definition, but basically the definition of vectors in multivariable calculus. Vectors in multivariable calculus are going to be a reinterpretation of points in n-dimensional space. Okay, so vectors are reinterpretations of points in multi-dimensional space, at least as far as our class is going to be concerned. Now, I want to mention that the reason we have the ability to think about points as vectors is that vectors require we can add them together, that we can scale them by coefficients, that zeros exist, and that the expected interactions of scalar multiplication and addition hold. Okay, so very natural ideas should hold with points in multidimensional space if we're going to be able to consider them as vectors. So what would it mean to add 2 points in multidimensional space? Well, we're going to put a plus sign between them. And how are we going to add the entries? It's exactly what you'd expect. We're going to add the first entry to the first entry. We'll get x1 plus y1. We'll add the second entry to the second entry, and we'll get x2 plus y2. And finally, we'll add the last entry to the last entry. We'll get xn plus yn. So adding 2 points together, you're just going to add each piece individually. And how are we going to scale, or how are we going to multiply by coefficients? We're just going to take this coefficient c, and we're going to distribute it to every single point. Distribute to every entry, meaning that we're going to take c times the first entry, c times the second entry, and c times the last entry. And how does 0 work? Well, 0 happens to be the point of all zeros. And if I were to add 0 to any other point in Rn, the output is going to be exactly the point I started with, right? Because of what we accomplished up top. If I add zeros to every single entry, I'm not going to change any of the entries. Now, this already probably feels very straightforward. I just want to formalize it and make sure that we both agree this is how you're supposed to add points in Rn, this is how you're supposed to multiply points in Rn, and then the 0 in Rn, the origin, does actually behave like 0. Anyway, what does that have to do with vectors? Well, it has to do with vectors. We're only allowed to represent objects like this or often we should only be allowed to represent objects like this as a single column array if they can be added element-wise, multiplied by scalars, and include a 0. That's when we're allowed to represent some other mathematical object as a single column array. And we call this single column array a vector representation. So what I'm trying to emphasize here is that we're going to stop writing points as kind of these parentheses with the variables separated by commas. We're going to start to represent points as single column arrays, and we're going to call those arrays vectors. So we will now represent n-dimensional points as column arrays and call these objects vectors. So now every time you see an array like this, there's a very slight chance it could be a single column matrix, but most often we're going to think about these arrays as points in n-dimensional space, but we're going to give them the name vectors. In this sense, if we want to add two of these points together and we represent them as vectors, we're just going to add straight across horizontally any two pieces together. So we'll get x1 plus y1, x2 plus y2, and xn plus yn. And if we want to multiply these vectors by a coefficient, we're just going to distribute the coefficient to every entry and recover cx1, cx2, cxn. Let's look at a couple examples of how we might multiply and add vectors together then. We'll go ahead and take the vector 1, 3, negative 1, multiply it by 5. How are we going to do that? Well, we'll just distribute 5 to all terms. What is 5 times 1? It's 5. What is 5 times 3? It's 15. And what is 5 times negative 1? It's negative 5. We'll do the same thing with the 2 over here. And we'll multiply it against a 3, against a 2, and against a 1. 2 times 3 is 6. 2 times 2 is 4. 2 times 1 is 2. And once we've computed each of these multiplications individually, following PEMDAS as always, multiplication happens before addition. So we're going to compute both the multiplications individually, and then we're going to add the vectors together. Let's recall we just add horizontally. We're going to add 5 plus 6 and recover 11. We're going to add 15 plus 4 and recover 19. We're going to add negative 5 and 2 and recover negative 3. I've got two more examples here of two-dimensional vectors being added together, or in this case subtracted, which we think about subtraction as a multiplication by negative 1. And so we've got negative 1 multiplying those two entries before we decide to add everything together and get our result. And technically we can even consider one-dimensional vectors, even though these behave like the regular real numbers, the one-dimensional real numbers that we work with. Technically you can consider them as vectors if you would like to, and you can still consider these vector operations on them. Naturally, we see with our vector operations that vectors of equal dimension are the only ones that can be added together. And so if we ever tried to add something like a two-dimensional vector to a three-dimensional vector, that's forbidden, or maybe a one-dimensional vector to a four-dimensional vector, that's also going to be forbidden. Anyway, we'll just practice in our exercises with these representations, and I wanted to give you all a good motivation for what linear algebra is trying to do. We're trying to solve systems of equations, or perhaps represent flat objects, line-like objects, planes, etc., hyperplanes in higher dimensions. This is the point of linear algebra. And then we represent all of these objects using matrices and vectors. And so we'll start to study more of the properties you can see ahead, matrix and vector products, start to study more of the properties of matrices and vectors in the next video. See you then.